Okay, this is a recording for the first part of, or at least one section of Moon, Chapter 2. So the scope of this class, the objective of this class is to develop tools that will be applicable in a wide variety of different settings. We will mostly focus on finite dimensional Hilbert spaces. Finite dimensional Hilbert spaces will include Euclidean spaces, Rn, Cn, and the set of, for example, complex matrices, C, M by N, or real matrices. Infinite dimensional Hilbert spaces will include the set of all functions with finite integral, or the set of all finitely summable sequences. Also, binary vectors, binary sequences, things like that. All sorts of different types of signals. It doesn't include important objects like rotation matrices, quaternions, homogeneous transformations, things that are used extensively in robotics. The development of the class, to make things clear, we're going to develop things in a systematic way where we'll do metric spaces, then norm spaces, then inner product spaces. And, if you were to do a Venn diagram, you would have metric spaces, and then norm spaces would be inside of that, which means that anything that's a norm space is also a metric space. And then inner product spaces, meaning anything that's an inner product space is also a norm space, is also a metric space. So if we develop tools that are applicable to metric spaces, they're also applicable in norm and inner product spaces. But if we have tools that are specific to inner product spaces, they may not generally apply to metric spaces. We'll spend most of our time inside here, inner product spaces, but the next couple of days we'll spend developing some tools for metric spaces and norm spaces. Okay, so what is a metric space? A metric space is a pair, X, D. Okay, so X is going to be a set of objects. For example, the Euclidean space. And then D is a function. Okay, so let's talk a little bit about this notation here for a second. So D maps X cross X onto R. And this probably we could put R plus here, meaning the positive real numbers. This means that, remember, the cross here is a Cartesian product. It means that that D is a function from two elements, one element coming from X, the other element coming from X, again, and it produces something that is positive real. Okay, so that's a metric. It's a function. Notice down here, our function is going to have two elements here, and this definition tells one is from X and the other is, both of them are from X. Okay, so a metric, again, we have the metric space is this set, and then also a metric. And a metric is really a measure of distance between elements in the set. Okay, so again, a formal definition. We have what is the metric? So let X be a set. Then the metric is this function from two elements of the set onto the positive real numbers. And a metric has to satisfy these four different properties. So this property, the first property, M1, says that if I have the distance between X and Y, that has to be the same distance between Y and X. So, makes perfect sense for real numbers or whatever. But they're, for it to be a metric space, the metric has to satisfy this symmetric property. Also, the metric has to be positive. So if we take the distance between X and Y, again, this metric has the intuitive definition of being a distance between, some kind of distance between X and Y. And it's going to have to be positive. Now let's talk about this symbol here. Okay, so this symbol means for all or for every. Okay, so what we mean by this this notation here is that the metric between X and Y has to be the same as between Y and X for every X and Y in the set. So it can't be true for just one or two or three pairs. It has to be true for every pair. So when we write this notation, it means for every single x and every single y inside of x, this has to be true. The second property is it has to be positive. The distance between x and y has to be positive for every single x and y that we pick inside of x. The third property, this says that the distance between x and y is 0 if and only if x is equal to y. So in other words, if x is equal to y, if y is equal to x, then the distance between x and itself should obviously be 0. But it says more than that because it's an if and only if statement. So we say that if the metric, so it's clear that if they're the same, then the distance should be equal to 0. And we're also saying that if the distance is equal to 0, they have to be the same element. The fourth element says that the distance between x and z has to be less than the distance between x and y and the distance between y and z. So think of, here's x, here's y, here's z. The distance between x and z has to be less than this distance plus that distance. And this last inequality is known as the triangle inequality. Okay, so these, if we can define a set and a metric that satisfies these four properties, then that is a metric space. Okay, so I have a number of different examples. So the first example is going to be, again, we have a set and a metric to get a metric space. So the set of real numbers, and then the metric that is just the absolute value of the distance between those 2 points. So again, we're on, the real line. Here's x, here's y, and this distance doesn't matter whether, x is less than y or y is less than x. That x is the metric. And you can see clearly that the first property here holds because the distance between x and y doesn't matter because of the absolute value. It doesn't matter which, whether you write x minus y or y minus x. This property holds because the absolute value, of course, is always positive. And so it's greater than or equal to 0 for every x and y. Again, for every x and y in the real numbers. And then the absolute value of x is equal to 0 if and only if, this should be an if and only if, x is equal to y. So if x is equal to y, this is equal to 0. And if this thing is equal to 0, then we know that x has to be equal to y. And the last element, you can basically convince yourself because if, for example, coming up to this picture, if z is up here, then this distance is going to be less than or equal to that distance plus that distance. And if, x, y, and if the picture looks like this, then the distance between x and z is going to be less than or equal to this distance plus that distance, obviously. So the set of real numbers plus the absolute value as a metric is a metric space. Another example of a metric space is Rn and then the mean squared error. So for example, if you're in R2, if we were in R2, the distance between the 2 points, x1, y1, and x2, y2, would be the sum of x1 minus x2 squared plus y1 minus y2 squared. And that's exactly this formula when n is equal to 2. Again, we can make the argument that this metric satisfies M1, M2, M3, and M4. Another example would be Rn, again, but a different metric. So instead of what we call, the 2 metric or Euclidean distance, we can have a distance where P here, P is not necessarily 2. In fact, we basically have the requirement that P is greater than or equal to 1. So all of M1, M2, M3 are relatively trivial to show. The fact that that this is true for every P greater than or equal to 1. In other words, the triangle inequality, the fact that the triangle inequality is true for every P greater than or equal to 1 is actually a famous and non-trivial result. So it's interesting because a metric, we can say, if P is equal to 1, this becomes simply the sum of the absolute values of all the elements. And, this says is a valid metric. If P is equal to 2, we get what we had before. If P is equal to 1.1, we get this interesting distance between objectives. We'll talk a little bit about this more when P is equal to, when we get to norm spaces, because this metric actually is a norm. So when P is equal to infinity, then this d of x, y becomes the maximum, I equals 1 up to n of xi minus yi, as we'll see. And we can show that, again, that satisfies the triangle inequality. So this is a metric space with that particular metric. Another example of a metric space is the set of bounded sequences. So let L infinity be the set of all sequences of complex numbers where each number is bounded. So in other words, if x is in L infinity, this should be like that, then x is going to be equal to a sequence, x1, x2, x3, x4, forever. So it's this infinite sequence. And each of these elements is a complex number. And the modulus of each of those, in other words, the square root of the real part squared plus the imaginary part squared, that has to be less than infinity. So if each of these elements here is bounded, then we can define this set, the set of sequences of complex numbers where each element is bounded. Okay, now if you define D to be the supremum of x minus y, and I need to take a tangent and explain what we mean by these symbols here. So first of all, the natural numbers, this is going to be the set, 0, 1, 2, 3, forever. So when we say J is in the natural numbers, J just goes from 0, 1, 2, 3, etc. Now, there are, sup here is equal to the supremum. And you can think of this as like the maximum, okay? But the problem is that there are functions that don't have maximums. So for example, think of this function, f of t is equal to 1 minus e to the minus t. Okay, this thing looks like the following. Here's 1, and it exponentially gets closer and closer and closer to 1, but never actually gets there. In other words, there's no t prime, there's no t prime such that f of t prime is equal to 1. So in other words, there's no t prime such that f of t prime is greater than or equal to f of t for all t, right? Because you pick any t prime up here, and you just have to go bigger than that, and 1 minus e to the minus t is just a little bit bigger, right? So it's getting closer and closer. So there's no maximum, right? There's no maximum. But you would look at this and say, well, the max is equal to 1. But a mathematician would say, no, formally there is no maximum. So what you have to do is define a new quantity. So the supremum is the least upper bound. All right, so like an upper bound would be, 2, would be an upper bound because f of t is always less than or equal to 2. But it's not the smallest upper bound because 1.5 is also an upper bound. And it turns out 1 is also an upper bound, right? F of t is always less than or equal to 1. And this is the smallest upper bound because if you picked 0.999999, then there is some t at some point that f of t gets above that. So nothing less than 1 can be the least upper bound. So 1 is the least upper bound. So you would say the supremum of 1 minus e to the minus t on the set t greater than or equal to 0. This is equal to 1. So because it's the least upper bound, where you can't, the maximum of 1 minus e to the minus t, t greater than or equal to 0, this is undefined. Okay, so think of the supremum as sort of a more general and a little more useful equivalent to the maximum. And on an equivalent note, you have the infimum, which the infimum. Okay, and this is the greatest lower bound. And this thing is going to be roughly equivalent to the minimum operator. Okay, but we're going to use, especially when we're taking minimums or maximums over infinite sets, we'll use supremum and infimum because those quantities actually exist, where a maximum or minimum may not be guaranteed to exist. All right, so back to our metric space definition. We have this metric d, which is going to be the supremum over all natural numbers of the distance between xi minus yi. So you just look one element at a time. You got this sequence of x, you got a sequence y. You compare those two. You take the maximum or the supremum, and that is going to be the metric. And we can verify that all of those satisfy M1 through M4. Another example of a metric space is the set of continuous functions on AB. So think of time and A, B. A and B could be equal to infinity, or they could be just simply finite numbers. And now we're going to think of the set of functions. There's a function, over a continuous function over AB. There's another one. Here's another one. There's another one. So these are all, in fact, this thing is a continuous function. Something like that would not be. So that's not an element of CAB. So CAB is the set of all continuous functions. So in other words, if x is in CAB, then x of t is a continuous function on AB. Okay, so this is a set of objects, and we can talk about a distance between functions. So one particular distance between functions might be the maximum of x of t, y of t. So here's t, and here's x of t, and here's y of t. So the maximum distance is going to be right inside here. There's some t prime. Let's suppose a and b. And so this maximum distance, it turns out to be a very valid metric for comparing functions. Now this kind of leads to a general theme that we'll be following in this class. In calculus, we thought of functions as, you'd consider one function at a time. In this class, we're thinking of a function as a point in a bigger space. So we have a metric space as the set of all continuous functions. Think of every single continuous function you could possibly come up with. And that it'll form a vector space, okay? And we'll be able to do operations on that space just like we do with, say, R2 or real numbers. That's the beauty of some of the things we're going to do in this class, is we're going to extend sort of these intuitive notions that we think of on the real line or in R2 to spaces like function spaces. Okay, another metric space is the discrete metric space. So let X be any set. So it might be the set of three-legged dogs, for example. So it's just a set, so you collect all the three-legged dogs in the world, and there's your set X. And then you've got what we call the discrete metric, which is basically the distance between X and Y is going to be 1 if they're not equal, and 0 otherwise. So you get 2 dogs, and if they're different dogs, then the distance between them is 1. If it's the same dog, the distance is 0. And you can show that this actually satisfies, obviously it doesn't depend on which dog you put in there first, and it's going to be greater than or equal to 0 because the only options are 1 or 0. And then it's true D, if and only if X equals Y. And the triangle inequality is obviously true because on this side, if X and Z are the same thing, we'd have 0. If they're not, this is going to be 1. If Y is the same as X, then this thing would be 1, and that would be 0. If X, Y, and Z are all different, then we'd have 1 less than or equal to 2. So it's clear that this discrete metric, satisfies M1 through M4, and so this becomes an example of a metric space. Another example of a metric space that is actually quite useful is the set of binary vectors. So let X be this. So what do we mean by this notation? This means, 0, 1 to the n is going to be 0, 1, Cartesian product, 0, 1, Cartesian product, 0, 1, meaning it's a 3 vector, let's say if this is to the 3, this X would be X1, X2, X3. And X1 is going to, it's going to come from this set. It's either going to be 0 or 1. X2 is going to come from that set. It's either going to be 0 or 1. And X3 would come from that set. So, for example, X might be equal to 0, 0, 1, as an example. Okay, so X will be finite dimensional in the sense that there's only a finite number of elements. Or it's not only finite dimensional, it's just a finite set. Now, the metric that we can use is something called the Hamming distance. So the metric, we're going to sum over every element. So we'll go 1, 2, 3. And if the elements are the same, we don't add to the sum. If they're different, we go ahead and add 1. So for example, if X was 0, 0, 1 and Y was 0, 0, 0, then the distance between X and Y would be the number of elements that are different, which would be 1. On the other hand, if Y is equal to, for example, 1, 0, 0, then the distance between X and Y will now be, there's 1 and 2 elements that are different. So this would be 2. This is called the Hamming distance, an example of a metric space. Okay, so later in the chapter, we're going to we'll introduce concepts of norms and norm spaces and inner products and inner product spaces. Some of the metric spaces that we just talked about will be norm spaces, and some will be inner product spaces, but not all of them. We'll talk more about that. Everything is a metric space, but we'll talk about kind of the difference between metric spaces and norm spaces and inner product spaces. Metric spaces are, again, the most general of the 3. And before we talk about norm spaces now, we're going to talk about some concepts that are applicable to metric spaces. So we'll do as many general tools as we can. We'll talk about topology, open sets, closed sets, things like that will hold in metric spaces, but not in, but will also hold in norm spaces and inner product spaces. And then as we get more specific, we'll start talking about norm spaces and inner product spaces.